record. Okay, so here, before I start your question, let me go ahead and answer somebody's question. So somebody sent me an email and she wanted me to go over, I'm guessing this was a quiz question. I had to go find it. I think I found it under quiz, but it's one of those bimodal questions where each one of us gets different kind of questions. And so, or different set of molecules or compounds. So in this case, she sent me a version of this question, which is this: identify each of the following. I guess they're all solids. It just said following, but wait, why is this not working? Come on. Hold on, my pencil tip got loose. Okay. Yeah, each of the following solids as. So the question they're asking you is identify the nature of the solid versus identify the intermolecular force. That's the thing with chemistry is even though we are talking about certain contexts, and that was intermolecular forces in chapter 11, you can't just assume that's what they're asking you all the time. So you really have to read the question and pay attention. So based on the answer choices, first of all, that you have, it gives you a clue. This is not about intermolecular force, because if it was, you would see words like dispersion, hydrogen bond, dipole. These are the answer choices we have. So let me actually say, A for atomic, M for molecular, and then I for ionic. None of these answer choices here go with the intermolecular force. So they're just asking you, in the context of solids, so I'm thinking this was chapter 12, right? These three are solids. When they are solids, okay, sorry, let me change that. When these are solidified, what types of molecules are we dealing with? I mean, what types of formula are we dealing with? They are solids, right? And so what would you say for Fe? Is it atomic, molecular, or ionic? And how can we tell? So let's start with the first one. If it is atomic, how will we identify that from the formula? They're all solids. All of these are solids. So these are hypothetical situations, right? Assuming that it's possible to make all of these solids. How can we identify something is atomic? How will atomic formulas be written? Anybody remember? This is more like 1411 kind of questions. The word atomic goes with what kind of formula? It's been a long time, huh? Elements. The word atomic usually goes with elements, not just elements, but usually monoatomic elements. I'm going to specify that and say monoatomic elements. So 1411, I specify that in chemistry, when they use the word atomic, they're usually referring to elements, but specifically monoatomic elements. Sometimes, depending on how casual the author is, they may use the term atomic to really even refer to molecular elements. Okay? When it comes to molecules, molecule is a term that's used to refer to both diatomic elements. Ooh, okay, this morning my spelling has been awful with my other class, so I assume it's going to be awful for the rest of the day, right? So excuse my spelling. The atomic elements and molecular elements. So what I mean by molecular compound. What I mean by that is the ones that are made up from non-metal, right? So compound from non, I'm running out of room. So the compounds that are made up of non-metals only, those are usually referred to as molecular. So if somebody doesn't want to be more specific, the general form, they'll use the term molecular. Okay. Last one, ionic tends to refer to compounds. And remember, this is compounds from, most of the time, metals and non-metals. So if this question boils down to the understanding of those definitions for 1411, okay? So having given us a quick review and a quick recap of what we covered in 1411, Can we then go ahead and classify our formulas based on the possible types? What do you think iron solid will be based on this classification here and the answer choices we have? Right. So this would be atomic, right? Remember, diatomic elements have that's the Brinkelhoff. Right here, Brinkelhoff. I know 1411 seems like forever ago. 1411 can't be forever. We need to bring it back, right? It needs to be right here, right now. So Brinkelhoff is the diatomic elements. They're the ones that are written, F2O2, H2CO2, N2, I2, Br2. Fun stuff. Okay, what next? What do you say about K2O? Is it atomic? Is it molecular? Is it ionic? You're trying to look for the classification, right? Ionic, right? Because it's metal and then this is non-metal. So yes, this is going to be ionic. Because it's metal and non-metal and it's a compound. This is definitely an element. What about H2O?
Molecular.
Molecular. Because this is a compound, right? Two elements. And then even though hydrogen is in group 1, it plays a role of a non-metal. So this is molecular, right? Non-metal, non-metal. This is element only, right? What about helium? This is also going to be atomic, right? Because it's an element by itself. And it's only one element. It's not part of the Brinkelhoff family, so you can't call it a diatomic. Now, in her question, oxygen wasn't there, but in the one that I tried in order to know what exactly was going on, mine had oxygen, so I brought it here as part of the conversation. What do you all think oxygen will be? It is O2. Any takers? Yes. No need to guess. We're talking about this one right here of the Brinkelhoff family, right? When you have an element, oops, my bad. When you have an element written in this format right here, the symbol and then sub 2, it's definitely a Brinkelhoff family member, right? And so that would be molecular. Yeah. Yeah, this used to mess me up when I was taking this way in middle school. And a little bit in high school. I'm not gonna lie, a little bit in high school too. Certain things hadn't crystallized yet, and I was still like, what's going on? Yeah. But once you recognize that the Brinkelhoff elements, these right here, they're usually referred to as molecules because you have more than one element attached together. Okay, now that I've answered that, now Jacob, I am ready for your question. Here, this is a space for you. Do you want me to put up a question?
Yeah, just it's a couple questions or about 3 questions. The homework question. Can you go to the last section? Question 9.
Wait, chapter?
Chapter 12.
Okay. See, you see how I had that ready? I had a feeling. I was like, you know what, we're gonna go here. Okay, hold on. So chapter 12, number 9, you said?
Yes.
So this one here? Okay. Oh, fun. Okay. So what are we working on? An oxide of chromium crystallizes with the following unit cell, okay? Oh, nice. So this is chromium. So chromium is gray and oxygen is red. What is the formula of the oxide? Okay, so chromium is gray. I have to remember that. So you have one, two, three, four, five, six, seven, eight chromiums, right? So we have for the oops, wrong writing utensils. For the chromiums, I see eight of the corner pieces, right? So 8 times 1/8 equal one chromium. I just write it as CR, okay? And then that takes care of the corner chromiums. One, two, three, four, five, six, seven, eight. And then this one here, it looks like it's in the middle, right? Because there's no shadows on it or anything. So that one is going to be a middle. So I have one center, 1 times 1. Oh, this is called a corner. And then center. And I see one chromium. So I have a total of 2 chromium ions, right? Is that what you got? You're like, let's see what
Yes.
you get. Okay, okay. I mean, let me make this a little smaller so I can write on the left right here. Okay. Then I have oxygen. I don't want to write the chromium ion because there are two different kinds of chromium ions that exist. Now, they didn't specify which one. The point is for us to figure out the formula from the unit cell, not from crisscrossing charges, right? They smart, they smart. Okay. With oxygen, when I look at this right here, I'm seeing a shadow that shows me that half of it is a different color. So I'm thinking these are one of those wall pieces, right? Face pieces. So I see 1, 2, 3, 4. Oh, this is tricky. They don't all look like face pieces. That may have been the issue. Hold on. Let me zoom in. Can I make this bigger? And there's no more dialogue here. Okay, let me try to make this real big because the issue here is I can't tell. Okay, maybe I made this too big. Okay, I should minimize this a little bit. But yeah, these two top ones are wall pieces. These two bottom ones are wall pieces. These ones here look like they are in the middle. So I only see 4 wall pieces. The ones that are on the face, see how they have two different colors? The top part, the top half looks darker than the bottom one, or at least it looks like a different shade. So, based on me trying to zoom in and zoom out, I think this is one of the things where you have to do by trial and error, okay? That I do have for the face, I see 4. 4, and the face is usually worth 1/2, right? So 2. And then because this looks like one color, it doesn't look like on the edge. This and this, I see 2 center pieces. So 2 times 1 equal 2. So this is 2 oxygens, 2 oxygens. I just say 2OX, 2OX. So I see 4 oxygens. So based on that, I have Cr2O4 divide by 2, divide by 2. I have CrO2. That's what I get based on what I see. This is one of those questions where the answer you get is based on how you're able to interpret the image. So let me type in here CrO. How do I do a subscript? 2. Okay. Now, can I just press return? Maybe not. Okay. Please be right.
Yeah, that's correct.
Yay. Yeah, the tricky part is this. Since I could see these ones on the edge here, yeah, on the sorry,
Yeah,
on the
that's exactly.
face, then that yeah, I could see that with these two. With these ones here, I couldn't tell. But since you see what looks like the bond or the attachment is going from outside to in, I had to assume it most likely was on the center versus being on one of the walls. If you have any questions, the exam will not be that complicated. Whatever has been picked or may, what's that word? Will be something that can easily be seen, not that convoluted. Okay. That was question number one. Next one. You said you had two or three?
Yes, it's on the quiz or the quiz. Can you go to the quiz?
Okay. Is this the same page as, oh, all assignments? Mm-hmm. 12? Am I working on 12? Quiz chapter 12?
Yes, correct.
Okay.
One and two.
Okay, so let me have this here to the left, and then the writing utensil here. Okay, so we have barium sulfide crystallizes in the cubic unit cell with S2 minus on each corner and each face. Okay, so we have barium sulfide and it crystallizes and you have S2 minus on each corner. So we know that there's S2 minus on each corner. That means that you essentially have 8 times 1/8 pieces. That will make one S2 minus on the corner, right? And then it says there's one on each face. So faces tend to be the walls. And for walls, if there's one on each face, that means you have 6. Each wall is worth 1/2. That will be 3 S2 minuses. Correct? Because it said there's one on each corner. There's 8 corners. The corner pieces are worth 1/8. One on each face. And that will be 6 faces, each worth 1/2. So I'm here. How many barium ions and sulfide ions are in each unit of barium sulfate? Barium sulfide versus sulfate. Okay? So they already gave you the empirical formula. The empirical formula shows you a 1-to-1 relationship. That means that the number of barium ions must be equal, right, to number of sulfide ions. How do I know this? From this relationship here. Since it says Ba1S1, that means the number of barium ions you have must equal the number of sulfide ions. So if we did this math and I got 4 total sulfide ions, how many barium ions should I have?
2?
They must be equal.
4. I'm sorry.
4 barium ions, right. So the ions are equal to each other. Because test it this way. If you said 2, if barium was 2, if barium ion was 2, essentially you'd be saying Ba2 S2 minus 2. I want to leave out these ions here because that confuses you with all these things. So if you said this would be Ba2 and then S4, then you divide by 2, divide by 2, you end up with BaS2. That's completely different than what they said than how they said they combine, right? Based on the empirical formula, we're kind of working backwards with them starting with this is the formula. This is how they combine. For every one barium that combines, it combines with one sulfur. So from here, essentially what we know is one barium ion combines with one sulfide. So if you have 4 sulfide ions, you need exactly 4 barium ions. So let's see. Yay, there. Because it's 1-to-1 ratio. If they gave you a question where it was 2-to-1 ratio, then you'd have to adjust for that too. It has to be 2-to-1. Okay, so we weren't figuring out the empirical formula. We're figuring out how many ions total based on the empirical formula they gave you. Does that make sense?
Yes.
Okay. That was question number 2. What's our number 3? Oh, yeah, this was the hypothetical situation, but yeah, this one from here we're back to BA4S4 divided by 4 divided by 4, which recreates the BAS, right? BAS. Was that a quiz or homework?
It was quiz number 2 for that one. I think
Oh,
you pretty much.
sorry, you told me. You told me. Listen, listen.
Huh?
I was so in the moment, I totally forgot. Okay, so here they're asking us how many F minus ions are around each Ag plus. Okay, so very similar question, right? So here we're trying to find how many F minus ions. What's the number here? And then they're going to tell us how many Ag pluses there are, right? And so for us to figure this out, they tell us how they relate to each other to the formula AgF. So based on this formula, essentially what we get from here is 1 Ag combines with 1 F. They have a 1-to-1 more ratio, right? 1 Ag plus F minus. Okay, so which has a cubic unit cell with F minus ions on each corner and each face. Now that I'm looking at the question and working out in detail, I'm like, wait a minute, isn't this kind of the same? Couldn't they mix this up a little bit, people? Listen, it's hard to write questions. It's not as simple as it seems. Okay, so for the F minus this time, oh, they're giving us the F minus information. Okay, so the F minus is on each corner. So corner pieces we know are
1/8.
the 8 times 1/8, right, to give us 1 F minus. And then the face pieces, it says each face, so that's going to be 6 times 1/2 to give us 3. So we have 4F minus. That means we'll end up with 4 Ag pluses and 4 F minuses, so that we can end up with Ag for F4 divide by 4 divide by 4 AgF, right? But they're asking you how many of it, yeah. Okay, so this should be 4.
Okay, thank you.
Oh, wait. Hold on a second. No. They're asking something different. I take it back. As I read the question again before I said submit, they're asking you how many F minus are around each. That's what makes the question different. Did you actually work that out and get an answer?
No, not yet.
So okay, so we have 4 AGs and 4 F minus, but they're not asking you how many of each is required. They're asking you how many of the F minus are around each AG plus. So even though we have 4 AGs and 4 F minus, I said one here, 1 AG combines with 1 F minus. So based on the way the question is written, each F minus should be around each AG plus. Okay, now I feel like maybe I'm overthinking this. Hold on just a second. Does anybody have a comment? I feel like somebody said something. Oh, Theo, instead of helping me out, you're laughing at me. No, because at first I thought the question was superficial, right? Now I'm thinking, you know what? I don't want to select the answer and then I get it wrong. They may be asking for coordination number because they're asking around each. Does anybody remember what the coordination number was for the cubic unit cell? This question is a lot deeper than I estimated. The more I read it, the more I'm thinking, no, they're not asking you how many of each one. They're asking you how many of the F minus ions are surrounding the Ag plus. This is a deep question. That's the coordination number. So you see the process I just did right now? You say put one. Okay, hold on. Let me see. Let me find the actual. I have to find the actual page now. I clicked so much, I forgot where it is. Okay, this is the other one. Yeah, hold on a second. For the unit cell, I think we had 6 coordination number, we had 8, and then we had 12. Right. So I'm thinking, after overly thinking this, which you have to do in chemistry, they're asking you how many Fi minus ions are around each Ag plus. I'm thinking it's gonna be 6. Okay? Because I'm overthinking this. Let's see what happens. And I was correct. I had to overthink it, guys, just because the more I read the question, I'm like, no, they're asking you something different. So here's the thing. This question is not the same as the first question. At first, when I jumped into it, I got excited and I moved. I was like, this is almost the same, but it's not. They're asking you how many F minus ions are around each Ag plus. So what they're really asking you is coordination number. You recognize that one Ag combines with one F minus, right? But they're not asking you how many combines with how many AGs combined with F minus. That's what I assumed at first, even though I read it. It took me, I almost selected 4, and then I realized, no, they're asking you surrounding. So remember we learned before that coordination number. So I'm glad you brought this up. This was a little bit of a challenge for me because I didn't read it for what it was saying. So what I just did right now is what you should not do. When you're reading a question, make sure you're present. I was still stuck on the previous question trying to relate the two versus reading this one here. Yeah. So when they're asking you, essentially they're saying that once you set up your structure, the Ag plus ion will be surrounded by the F minus, right? And I won't even try to draw this because I'm not very good at drawing this. But I'm going to go back to the slides to show you this. Since they told us it was a cubic unit cell, you want to go back to the cubic unit cell and see how that looks. So I'm going to do that so I can show you how I figured this out too. Go back here to the course assignment because that was a tricky question. And if you're actually going through and clicking from one answer choice to another, you're not really understanding what they're asking you, right? If you click through 4 times when I've given you 10 tries, you're just really guessing your way through it. So let me go find the picture that shows you the different unit cells and their arrangements. Yeah, that was a tricky question. It was actually fun. So the description they gave us was the cubic unit cell, right? Talking about you have atoms here. They were essentially describing this in words. So even though it was hard to tell, by them giving you the cubic unit cell, this is where your mind should have been. This is where my mind was at first, that we have 8 corner pieces. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have 6 face pieces. So you have the ones on the face. And then they're telling you now, if the middle one is silver Ag, how many fluorides are surrounding it? Because I kept thinking of the question as I was reading it. And then that's when finally I thought about it and realized they're asking you for the coordination number. They didn't use the term coordination number, they just described it. Does that make sense?
It
By
does.
them giving you the name, then you had to focus on this. If they had asked you the same question and they gave you a different one here, you have to come back to this slide and ask yourself, if your central ion they're asking you about, if it was elements, the same combination, but you had silver right here and they asked you how many fluorides are surrounding it, you will answer the number of fluorides based on this body-centered cube, if that's how they asked it. That was a decent question. So now I see why I picked it. I picked these questions a long time ago, so it's been a while. I've forgotten about half of these. But yeah. Any other question?
No, that's it.
Oh, okay, great. I'm glad we figured it out eventually. Let's see. I was like, just pick one. No, I didn't want to get it wrong because I was like, nah. Not that it's counting against me or anything, but it does feel better when you get the correct at once. But yeah, with chemistry, you kind of have to really pay attention with the question and the words that you're using. And it's hard to kind of switch that off. I kind of usually read too much into things when I'm not doing chemistry and I'm told I'm reading too much into things, but that's what you do with chemistry. Okay. So unless you guys have another question, let me go ahead and delete this page and start with a new chapter. So this new chapter is about solutions. And ignoring all those pages there, this chapter is about solutions. Now in 1411, depending on where you took it, you should have covered solutions a little bit, talking about molarity and all that stuff. We talked about the stoichiometry that had to do with solutions. So we're going back and looking at solutions over again, but this time we're spending more time in the details. Okay. So we're told solutions are a homogeneous mixture. Homogeneous means that when you look at it, you can't tell it's a solution, but if you're able to analyze the sample, you will find out it's a solution. And it has two or more substances mixed up together. Okay? Your solution can be made up of two solids, so you can have a solid and solid solution. Yeah, we have that in chemistry. Liquid and liquid, gas and gas, or even combined across, right? The most common solutions we talk about are solids and liquid solution. But right now, as we are all sitting here talking and hopefully inhaling, we are inhaling a solution of gases, right? What we call air is technically a solution of gas. Why is it a solution? When you look at the air, you can't tell that it's a mixture. You know it's a mixture from experience or from reading about it. When we talk about solution, it's important to know the solute and the solvent. Solute is the lesser component, solvent is the greater component. So you want to know the difference because when you're working out the equation, in 1411, I mentioned it's important to know the difference. In 1412 is very critical because when you're doing your math, for example, trying to find molarity, we'll figure out the moles of solute over liters of solution. So you need to know if the number they gave you in the question is a solute, a solvent, or a solution. Okay, so these words become important when it comes to doing the math problems. Okay, so let me go ahead and, where am I? Right here. Let me add a page. I'll quickly define the different components. Once again, you have solute. This tends to be the lesser amount. You have solvent. This tends to be the greater amount. And then you have solution. Solution is usually solute plus solvent. Okay, the mixture of the two. For the most part, the physical state, I've been asked this before. Well, what's the physical state of a solution? The physical state of the solution tends to go with the greater amount because there's more of it, right? If you mix 1 drop of blue with a whole bucket of yellow, so 1 drop plus a bucket of yellow paint, the overall paint will look yellow, even though you added some blue there, because you have more yellow paint than blue. So the dominant amount, the greater amount, tends to affect the physical appearance of the solution. Okay, so just in case you're thinking about that. Now, for us to make a solution, we're told that there's a prerequisite. There has to be a requirement met. In a solution, to form a solution, we're looking at likes dissolves likes. So we're going back to chapter 11 and saying, don't forget the intermolecular forces of attractions have to be similar. They don't have to be exactly equal, but they have to be similar, or we can say compatible. Okay, so we learned in the previous chapter for intermolecular forces, if you have a nonpolar solute, this tends to dissolve in nonpolar solvent. Okay, this is summary from chapter 11, right? We gathered that nonpolar solute dissolves in nonpolar solvent. Nonpolar solute will not try to dissolve in anything else but something that's just like it. So I would say the one that tends to be the most trickiest or restricted is that one. And then polar solute dissolves in polar solvent. Pretty straightforward, right? Now, I didn't say same, I said the word similar, right? The ones that kind of can dissolve across, that would be ionic solute dissolves in polar solvent. Okay. Does anybody have any questions about that? So this is what we learned from chapter 11. So we're bringing that knowledge here because we need that here to carry on and talk about solutions. We need stuff to dissolve to make a solution. Anybody have a question about ionic and polar dissolving each other? Okay, I'll ask a question because I am one of those skeptical students, right? Hold up a second. This is me talking to myself. Nonpolar, I get. Polar and polar, I get. Even the words match. But ionic and polar, what? Okay, so this is me as a student and me as a teacher. Dealing with the ionic compounds essentially have that bond that used to be polar, but it broke up. So I'm going to give you guys an example. Table salt. The bond between sodium and chloride, once it's broken, forms sodium with a full positive charge and chlorine with a full negative charge.
And
Okay? We
ionic
know
also has dipole, correct?
ionic?
Yes.
No, ionic only has ionic. It is the polar that has dipole. I see where you're going with that, but the polar has dipole. Ionic is seen as an extreme polar, but it's not considered to have dipole. So I kind of see where you're getting that thinking from, that ionic bonds are seen as extreme polar, but in this context, people don't define the ionic bond as a dipole. It's called ionic bond. So you don't confuse the two. Remember in chapter 11, we said when table salt dissolves in water, so here I'm going to use water to represent my polar molecule, water right here, dot, 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 dot. I'm talking about just the one bond, not both of them. This one bond here, this bond is polar, right? Even though it does do hydrogen bonding, the thing that connects the two of them and allows them to dissolve in each other is the polarity of the bond. So going back to 1411, oxygen is more electronegative, so it gets the partial negative sign, not fully negative. Hydrogen gets the partial positive sign because only when the bond breaks does the hydrogen become fully positive and the oxygen fully negative. As long as the bond continues, which in this case the bond will remain, hydrogen is partially positive, oxygen is partially negative. So how do these interact with each other? The opposites attract, these opposites here attract. The full positive from sodium attracts the partial negative from oxygen. Even though it's not full negative, they're still oppositely charged. That's how we get the ion from here, dipole interaction. One of them is an ion, the other one is a dipole. Okay, so I just reviewed the ion dipole interaction. So ionic solutes will dissolve in polar solvents. The good thing about 1412, we review 1411 so much, you feel like you took both classes over again. Okay? And then we review different chapters and new chapters. That's what makes it a little bit, 1412. You know what I mean? Okay. So, you guys did this based on the question I asked you. We talked about CH3 CH2OH. And I told you that this dissolved both in water, right? And it dissolved also in CCl4. We mentioned this in the last session. Remember, a molecule like an alcohol, this being our solute, if this is our solute right here, we're trying to dissolve it in two different solvents. This is solvent one. The first solvent here is characterized, it's called polar even though it can hydrogen bond. This one here is a solvent and it's called nonpolar because it's nonpolar. This solute here, ethanol, has two behaviors. So I'm going to highlight this. It has a polar region. This part here is a polar side of the molecule called the polar region. And then the rest of it, let me give it a different color. This part here is nonpolar. So guess what? This solute here, it can dissolve both in the polar region or polar solute, and it can dissolve also in the nonpolar. So we'll see that down the road. Let me actually get you that down the road area. Okay, so when one substance dissolves in another, it's said to be soluble. Like we saw right here, salt is soluble in water. Remember we said salt is ionic, and then water is polar. So when these dissolve, they're using an ion dipole way of dissolving. Okay, the salt, usually the ion interacts with the water. So the water plays the role of polar. The salt is an ionic compound, so it's the ion, and that's how they get together, right? Here they're telling you bromine is soluble in methylene chloride. So once I began to see that chemistry was very trendy, when I say trendy, I don't mean like it's trending, but it has a lot of trends, right? A lot of similarities, a lot of patterns. I should say, okay, there's a lot of patterns in chemistry. When I was reading even new information, I was always asking myself, what's the pattern they're trying to illustrate here? They're showing us bromine. Remember, bromine is a Brinkerhoff. Bromine is soluble in methylene chloride. Now, you probably don't know the chemical formula for that, but it's CH3Cl, right? Now, with this right here, for the most part, the methylene chloride here, since bromine is going to be nonpolar, then you can conclude this one right here is also nonpolar because bromine is nonpolar. So they give you an example here of ionic and polar, and then nonpolar and nonpolar. And that's the biggest thing you need to get from here. When you try to crisscross two intermolecular forces that are not compatible, for example, in this question here, when one substance is not dissolved in another, it is said to be insoluble. Most likely, you try to make a solution with two chemicals that do not have a compatible intermolecular force. For example, in general, oil is nonpolar. Greasy chemicals tend to be nonpolar. And then water, we just said so many times, is polar. So you try to mix a nonpolar chemical with a polar chemical. So when this happens, they do not mix. I had this experience once though, y'all. Man, life experience to me personally is awesome. So I had a chance to go to Mary Kay, right? And it was a tour most of the time for the district, Dallas College. They have all these tours for students, but they said, you know what? We're going to take a few teachers. I used to be a mentor for different students on different campuses in the district when we were a district, now college. They gave the mentor instructors and the students a tour to Mary Kay. While I was there, they had all the instruments, equipment we have in lab, but everything was huge. So the scientist giving us a tour was talking about polar and nonpolar. And she's saying that we have oils and water in our chemicals, the liquid ones, the lotions and stuff. I'm like, polar, nonpolar. I'm thinking in my head, trying not to sound like a nerd, but I'm like loving this. And then she says, but when we're trying to make creams, we can't have layers because it doesn't look appealing to the customer. So we have to find another chemical to reconcile this two. And so she said the chemical is called the emulsifier. Oh my goodness. Okay, I forgot what the spelling was. Let's call this emulsifier. Anyway, I was like, oh. So the great thing about science is even though we know the natural behavior of chemicals, we're always trying to find ways to counteract that, right? Naturally, nonpolar and polar solutions should not mix or should not even be formed. But if you can find an emulsifier, the emulsifier will try to force these two to form a pseudo solution, right? So naturally they wouldn't mix. Sometimes you can even use a physical process to mix the two. Like if you beat butter and eggs and water to make a cake, the act of using that, what's that thing called? The mixer, the electrical mixer, forces them to make a pseudo solution. Okay. But naturally, if you add these two together, they will not form a solution. You have to add a third entity to force that to happen. Okay. So we're told that for the most part, when you're dealing with solids and liquids, so I'll say here for solid plus liquid solutions, the solubility of one substance in the other can vary with temperatures. With solid and liquids, if you increase temperature, it increases solubility. And if you cook, this chapter will be fun for you because then you have a lot of personal experience with these. There are many, well, there's not a lot of things I cook that does this, but sometimes I see certain recipes where they're trying to dissolve a solid in the liquid and they say heat and stir to dissolve. And I'm like, they're trying to increase solubility by increasing temperature, you know? And so we're told here more solute can be dissolved in the solvent by increasing the temperature or increasing the pressure if the solute is a gas. So we will talk about this down the road dealing with Henry's law. So they give you a quick review of chapter 11. Remember dispersion forces, chapter 11, in forming a solution. You have one of these being the solute, the other one being the solvent. Example, heptane and pentane. Once again, remember organic compounds that have no heteroatoms. Organic compounds that have this format, CXHY, where these can be any number. They have just two elements, carbon and hydrogen only. These tend to have dispersion force as their only force. We've seen dipole-dipole. As long as you have molecules that are both polar, and these are both polar, these will tend to bond or form solution using dipole-dipole interaction. Here, the form of interaction, since they both have OH bonds, right? Hydrogen being the double OH molecule. These will use hydrogen bonding to bond. And then finally, we see the ion dipole again. Remember, the ion here will have to be an ion from the ionic compound. And then the dipole is the water, which is essentially polar. So from from chapter 11, we get to see these again. Okay, so these are four different ways of forming a solution. Now we're dealing with organic compound solubility. So what I explained to you earlier about CH3, CH2OH, I used to have a chart in the old book, but they kind of gave us an upgrade, and I don't see the chart here, so it's kind of explained in words here. Okay, I explained to you that organic molecules such as alcohol has both polar ends and nonpolar ends. I just said that right now. This is going to be the polar end. And then you have the rest of it, that's a nonpolar end, right? So what's happening in the organic molecule is sometimes depending on how many carbons you have, the nonpolar end will begin to compete with the polar end. For that reason, we're told here, organic compounds with 5 or less carbons, I'll actually say, yeah, 5 or less carbons will, for the most part, dissolve in water. Organic compounds with 6 or more carbons will dissolve in nonpolar solvents. So when you start to have 6 carbons per 1 OH, that's not being explained very well here. So you need to have 6 carbons per 1 OH. If you have this criteria met, then this organic compound begins to dissolve in water more. Dissolves, in non-polar solvent. So the idea here is if you have an organic compound with 1 carbon per OH, it will dissolve in water. 2 carbons, 3 carbons, 4 carbons, 5 carbons. Once you start having that 6 carbon, the 6 carbon parts, now the nonpolar region starts to dominate. So let me try to illustrate that here, and that way it will summarize this. I'll add a page and show this real quick. So I'm not going to fill in the hydrogens just for the sake of writing fast. So I'm going to show you 1 carbon per this right here. Then we have 2 carbons per 1 OH, 3 carbons per 1 OH, 4 carbons, 4 carbons, 2, 3, 4. Okay, so we're told here that all of these are in water. Okay, for each of these you have this one here, you have 3 H's missing here, and the rest of them, the H's are wrong. Remember, each carbon has 4 bonds, right? These are all soluble in water, but as the number of carbons increase, the nonpolar region of the alcohol begins to dominate. So this is the cutoff point. Once you have 1, 2, 3, 4, 5, 6 carbons per 1 OH, this one here is now considered, because of all these carbons, this molecule here, whatever it is, does not dissolve in water. Why? The non-polar region becomes more dominant. Okay, so this part here now characterizes the compound because you have more carbons per OH. Okay, any questions about that? Okay, so the cutoff point is 5. Once you get above 5, now we're dealing with nonpolar, right? Okay, so let me make sure. Yeah, so once again, alcohols with 5 or less carbons for each OH will dissolve in water. As the number of carbons increases, we have a less polar nature. The solubility in water will decrease, but solubility in hexane, the nonpolar solvent, will increase. So let's go and look at vitamins. If you take vitamins, so at the time of Corona, we're told, take vitamin D and other vitamins and vitamin C. Okay, let's examine this as far as chemistry is concerned and solubility. We're told here, and I learned this in biology also, vitamins are categorized as either fat soluble or water soluble. Water soluble vitamins dissolve in the bodily fluids and are easily eliminated in the urine. So there's little danger of overconsumption. That's if you're drinking enough water. You want to make sure you're drinking enough water so you don't overdose on the vitamin or have too much in your system, right? You have to be flushing it out by drinking a lot of water. Fat-soluble vitamins, on the other hand, can accumulate in the body fat deposits because fat dissolves fat, or nonpolar dissolves nonpolar. The fats in your body are nonpolar, oil-like, right? So as those fat-soluble vitamins. Overconsumption of a fat-soluble vitamin can be dangerous. Examine the structures of each vitamin shown here and classify it as either fat-soluble or water-soluble. Okay, we can do that. What was the rule again that we just learned? 5 carbons per 1 OH. That's the cutoff point for water solubility. right? That's a summary of all the words I said for the previous slide. If the vitamin is going to be soluble in water, for every one OH or for every polar bond we see, it can handle up to 5 carbons. Okay. What do y'all say about vitamin C? Is vitamin C water soluble or fat soluble?
Water soluble.
Okay, based on experience, we can confidently say water soluble, right? Because your mom is like, oh, take some vitamin C, and if you have those gummy kind, you take 2 when you're supposed to only take 1, and you're fine, no big deal. But when you take the other ones, I was about to say what it was, I can't say because we're working on these right here. Okay, let's see the chemistry. At least count the OHs. 1, 2, 3, 4 OHs. You can count these 2, but I'm trying to keep it simple. So based on the OHs only, 4 OHs, this can be water soluble if it can handle up to 20 carbons, right? And then if you have the 21st carbon, then it starts to be maybe insoluble. So let's see. You got 1, 2, 3, 4, 5, 6. Man, this is highly soluble. Not just soluble, highly soluble. But you got to drink a lot of water, right? So it has something to dissolve in. Okay. So highly soluble in H2O, I forgot. Vitamin K. So vitamin K doesn't have OH, but all we need is the polar bond. So even though it doesn't have OH, we're looking for the next best thing, which is going to be this bond right here. C double bond O. This is polar. And now what we're trying to find here is for every polar bond, it can handle up to, once again, 5 carbons. Okay? So since we have 2 polar bonds, then these 2 polar bonds can handle up to what? 10 carbons? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oops. Just missed it by a little bit. But there. So what do you guys think? Is vitamin K going to be soluble in water or in a nonpolar solvent?
Nonpolar.
Okay. So this one here, of course, will be fat soluble because it can dissolve in anything nonpolar but not water. It missed it just by 1 carbon. All we needed was 10 carbon, but it missed it by 1. Okay. So when we get done with this, I'll show you the biology version. I remember taking this in biology and having to answer one of those multiple choice questions. Which of the following vitamins are fat soluble? So we have water soluble right here, fat soluble, and then vitamin A. Look for either OH. The next best thing is the carbonyl. Oh, come on. Okay, we have 1 OH. 1, 2, 3, 4, 5. Is there any point in counting on beyond that? No point. What is this one here? Does it dissolve in water? Okay, dissolves in fat or anything nonpolar Plus, we know vitamin A to be an oil, right? Or very oily, right? Because look at all of that. The CHs are essentially fatty. So yeah, in fat or anything nonpolar. What about vitamin B? Okay, so let's find the OHs first. We got 1, we got 2, we got 3. Okay, and if you want to, you can include this one here, 4, 5, and remember this one here also does hydrogen bond 6. Okay, so all of these can help to form that solution. So based on that, how many carbons do we have compared to all those we circled? 1, 2, 3, 4, 5, 6. So 6 should be able to handle 6 polar bonds. Should be able to handle how many? 30 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all I see. So definitely less than 30. So this should be soluble in water, right? And we know vitamin B to be soluble in water. Usually the more common vitamins taken are soluble in water. That's the one that you don't have to call your doctor to ask Can I take this? The ones that you have to call your doctor, they're written on there, right? So soluble in water, or we can call it water soluble. Was that it for the question? Oh, yeah. So in biology, usually they say ADEK. So I memorize it as ADEK. Vitamin A, D, E, K. That's the one you have to call your doctor about before you start taking. Because if you take too much, it will store in your fat cells. There was actually one scenario, one situation where someone was taking a lot of vitamin D and then they try to work out to lose weight. Like it's totally unrelated, right? You're taking a lot of vitamin D, you're trying to work out to lose weight. Yes, exactly. You're trying to work out to lose weight, right? All of a sudden they're having some kind of symptoms. They go to the doctor, you increase vitamin D intake, you're trying to decrease your weight, and all of a sudden they're having these symptoms of feeling sick, and the doctor says you have too much vitamin D in your system, is messing you up. How did that happen? I was taking just the right dose of vitamin D. What was happening? And so unintentionally, the vitamin D not only increased in the system, it also resulted in an increase in cholesterol. Sadly, we don't discuss this in this chemistry. We discuss this in organic chemistry, but I'm just going to tell you too much vitamin D can sometimes, not all the time, sometimes with certain people affect the cholesterol because the cholesterol structure has, if you look at it, it has similarities with vitamin D. So as they were trying to lose weight, the losing weight meant that they were actually breaking down the fat molecules, and the fat molecules was releasing vitamin D into their blood. I mean, it was like an interesting mystery for me. I'm sorry, I like mysteries, even in medical mysteries. So they were losing fat as they were losing weight. The fat was releasing the vitamin D that was stored in there. The vitamin D was adding to their vitamin D and therefore increasing cholesterol. It's complicated. That's why medicine is complicated. It's not that simple. Science is, to me, science is a lot simpler because you're dealing with one thing. Medicine, you got to put it all together and deal with health, right? Complicated. Okay, so now we're moving on to solubility. You can tell I enjoy this, right? Somebody told me one time, I can tell from your voice you love this. I'm like, of course I do. It's my job. Okay, now we're dealing with solubility. Solubility, once again, I can tie it back to health and a lot of things. Solubility is the maximum amount of solute that can dissolve in a specified, but each amount of solvent. And that is essentially called solubility. So for each amount of solvent, a specified amount of solvent, so I think I like the word specified more. If you have a solvent, so let me give you an example here. I have a solvent, a liquid in a container. This one here has a larger amount. The next one I'm going to draw will have less. This is less. By default, the one that has a larger amount of solvent, this one here can hold more solute because there's more liquid, right? This one here holds less solute. I have nowhere to write the word solute. That's how much smaller it is. Okay. So we're told there is usually a limit to solubility of one substance in the other. Okay. We're told here gases are always soluble with each other. Due to the whole lack of intermolecular forces and stuff, gases don't have to interact with each other to dissolve with each other. They just kind of occupy similar space, right? So gases always mix with each other. But for liquids to mix with each other, remember the intermolecular forces have to be similar. Alcohol, water, this is polar, polar, right? This is going to be dipolar. Oil, water, we have polar polar for water versus non-polar for oil. And of course, these ones here won't mix. So we're being told here solubility, of course, is influenced by temperature and pressure. This is kind of repeating what I just said, so I won't go over that again. You can read that on your own time. I want to talk about solubility limit. Remember we said each solvent can hold so much. So the solubility limit, There's such a thing as adding too much solute in a solvent when you're trying to form a solution. A solution that has the solute and the solvent in dynamic equilibrium is said to be saturated. So we're learning this new terminology, saturated. So you have the solute and the solvent in dynamic equilibrium. So in chemistry, you see this term a lot. I'll say chemistry, sometimes biology and physics. So I went from hating it to being indifferent to it to where now I'm like, okay, I can tolerate it. So I think I'm still at indifference. I don't say I love this term, but dynamic equilibrium just means that one direction matches the opposite direction as far as flow is concerned. Okay. So you have just enough in solvent so that equilibrium. That means movement. Okay. So let me go ahead and describe this from the point of view of movement when you're making a solute and a solvent into a solution. So the idea here is solution. Okay. A solution is made when you have a solute added to a solvent. Okay. So when the solute is added to a solvent, let me say we have a lot of solution here. So I'm going to draw the solute molecules in red. These would be my solute. And then my solvent molecules in blue. Okay. So the idea is if they're interacting well, these are my solvent, to form a solution, then we have dynamic equilibrium. Now, if they're not interacting very well, what that means is solvent molecules are kind of just staying by themselves. And then the solute molecules are staying by themselves. Having is layers separating the solute molecules from the salt. Okay. I just thought about an analogy. When I was in school before college, I won't tell you when, but before college, we used to boy dance. You know how that goes. And the girls are in one corner of the room talking to themselves, giggling, whatever, and guys in one corner. So that would be like a situation dynamic equilibrium because you have some kind of segregation by gender. Girls in one corner, boys in one corner. Comes in there and says, "Come on, dance together," and then they all of a sudden you start having people moving around. The mixing is happening, and when the mixing is happening, you go from separation to good mixing. Now, when they're saying is dynamic equilibrium, that means that occasionally some solutes and solvents are going back to being separated, but then some are also going back to mixing. Okay, so let me try to draw this. So on one hand, you have the mixture. Oh no, what happened? Oh no, sorry, I didn't mean to just leave. Give me just a second. Let me reshare this. I think they heard me talking about a boy and girl dance. Anyway, so can you see it by screen now?
Yes.
Okay, so you have mixing and you have separating going on. So at the same time, you have molecules mixing, and then some are going back to separating. So you have both situations happening. A few are separating and a few are mixing. So the equilibrium shows that both are occurring at the same time. Some of these molecules remain separate, some of them are mixing, and as long as you have a flow both ways, that's dynamic equilibrium. Okay? So once we see that, if you have just enough solute in the solvent, That's considered saturated. So I want to spend time discussing saturated. Saturated, hold on. My pencil is glitching. Whole screen shut off. Now my issue is the pencil. Oh no. Give me just a moment. Okay, I'm not too far. Okay. Oh, there, it's working again. Woo! Technology, we can do this. Okay. So saturated solution is essentially a solution that has the maximum amount of solute present. Okay, this is saturated. So many times I hear in the English word saturation referring to liquid. There's so much liquid in a sponge or something like that, or you're trying to absorb liquid somewhere else. But I hear the term saturation a lot talking about liquids, right? But the context here is the amount of solute in the solvent. Okay, you have the maximum amount of solute. And then if that's saturated, then unsaturated solution. Now, I'll give you guys a mathematical example of this one here. This one here is a solution that has less than maximum amount of solute present. That means there's room for more, right? There's room for growth. Okay, so based on this logic, you have saturated, you have unsaturated. What do you think supersaturated is? Supersaturated solution. What do y'all think that would be? Based on this logic we've been on. Saturated, unsaturated, supersaturated. Anybody want to try to define it? And then I'll explain to you how it happens. So we know all three are solutions, right? But what behavior does the super saturated solution have? Any hypotheses of any guesses of what you think the definition would be? I know it's a solution that has how much solute? More solute than the maximum allowed. So how is that possible? If the first one had maximum, how can you have more than maximum? Are you violating some kind of code? There really isn't a code to violate because science is all about violating codes, right? No codes like, safety code, but it's all about trying. We learn the rule only to see if we can bend it, right? I'm smiling as I say that. For real, we're learning. Saturated is the comfort level of the solution. If you add a solute until the solution is saying, okay, this is enough, that's saturation, the comfort level of the solvent. And then, of course, unsaturated, you haven't even reached that maximum level. Supersaturated, you cross the maximum level. You went to the maximum level and did stuff to force the solution or the solvent to accept more solute than it naturally can. So we mentioned earlier, we can influence the nature or the capacity of the solvent by temperature. So to make a supersaturated solution, all we do here is increase temperature of the current solution, or I'll just call it solvent, to accept more solute. Okay, that's all we're doing, adding more heat to the solvent to allow it to accept more solute than it normally would. And in doing so, you make a supersaturated solution. Any questions about this? So they're showing you here in the picture, and this is the solubility limit. So this picture, all these three pictures here show you a supersaturated solution. This is a more solute than saturated, or the saturation point, right? So you force the solvent to take in more solute than is normally used to taking in. So let me try to explain this mathematically, okay? Let's say for what here, the saturation point is 20 grams per, this is obviously a salt, so 20 grams of salt per 100 grams of water. Okay, this is saturation point. That means at that temperature, whatever the temperature is, let's say room temperature, you can add up to 20 grams of salt per 100 grams of water. Okay, now we're dealing with this right here. So if this is our standard, what if I want to put in 35 grams? So I have water, I have 100 grams of water, and I want 5 grams of salt. Obviously, the desire I have does not match the comfort level or the capacity of water, right? That can only naturally grams of salt, but I want to put in all 35 grams. So what do? I add 20 grams. I heat up the water, or you can heat up the water and then add all 35 in there and force all the solid. You stir it as you heat it up, and the water will, because of the heat, will accept all of it. So what they've done here is they have made a supersaturated solution, and you can't tell it's supersaturated, right? Because it looks like any other solution, supersaturated right here. And they have slowly cooled it to room temperature. This is slowly cooled, carefully, slowly and carefully cooled to room temperature. And at room temperature, it looks like any other liquid. Actually, it could look just like the solvent, right? But we know it's supersaturated because of what happens next. Supersaturated liquids are very unstable because they're uncomfortable because they're holding 15 more grams of salt than they can hold, right? 15 more grams, 15 extra grams of salt. So they're very unstable. If you knock it by mistake, or if you add a speck of dust or even anything, if you disturb it, all of a sudden this begins to happen, and the supersaturated solution begins to dump the 15 grams. It crystallizes. And the way it crystallizes is it starts to dump out of solution that extra 15 grams it was forced to hold. And so here you get a crystallization. So for those of you who are going off to organic chemistry, organic chemists use this method to purify compounds. Once they make the compound in the lab and they want to purify it, they'll take the compound, dissolve it in water, or most of the time it's in water. And once it gets dissolved, they will actually use crystallization. They'll call it recrystallization to get a purer form of the chemical. Okay? So this is the first step. So once you're making the crystal, the original solid was a crystal, so they'll call it a recrystallization. You're remaking the crystal, but whenever the crystal gets made, it's now pure. So here in this picture, we're told that for the most part, solids will increase in solubility as temperature increases. That's what we're being told here. So you want to look at the solubility curve. Everything here increases in solubility as you increase temperature. Temperature is going from 0 to 100, right? solubility increases. And here, once again, this is solubility. So the y-axis is showing you the amount, the grams of solute that can dissolve in 100 grams of water. So let me ask you some questions because you want to know how to read this graph. It's an important part of this, of the learning outcomes. Okay, so I'll ask you for temperature at 70 degrees Celsius. What's the solubility of KClO3? Remember, this graph is showing you the solubility of different salts at different temperatures. So just based on this graph, what is the solubility? How many grams of KClO3 can be dissolved in 100 grams of water? So what is the solubility of KClO3 in water? Okay, so you want to go ahead and the temperature is 70 degrees Celsius, right? So you want to go up here, up, and then read this. Very good. 30 grams. So what you're saying from this graph, 30 grams of KClO3 dissolves in 70 degrees Celsius of what? 70 degrees Celsius temperature. And the amount of water is 100 grams of water, right? Remember, this amount is always in 100 grams of water. So that's how you will read that graph. Okay? So the other thing I want to talk about here is if we know 30 grams of KClO3 dissolves in 70 grams of water, what if I told you I had 30 grams of KClO3 in a solution? That means that all of it got dissolved in there, but the temperature is now only 50 degrees Celsius, not 70 degrees Celsius. Or you know what? Let me make it room temperature. The temperature is 25 degrees Celsius, but I managed to get all 30 grams of KClO3 to make a solution. How would you describe this solution? What name will you give this solution here? I got 30 whole grams of KClO3 to dissolve in 100 grams of water. That's what they mean when we say solution, right? But the temperature of the water is not 70 degrees like we saw. The temperature of water is only 25 degrees. What name will you give to that solution? Is it unsaturated? Okay. Yeah, it's oversaturated, right? So supersaturated. Because it's more than what it can handle at that temperature, right? So supersaturated. It's more about how much it can normally handle. If it's way more, but I keep trying to convince you this is a solution though, and that means that if I manage to make it dissolve, we're talking about a supersaturated solution. Okay, very good. So now we're looking at solubility of gases in water. How do we make those bubbly drinks, the sparkling cider and all that stuff? The example we're seeing here in the picture is cold soda pop versus warm soda pop. So soda, right? Cold soda produces less bubbles. Warm soda produces more bubbles. So we're talking about gases dissolving in water, right? We're told in general, gases in general are nonpolar. Think about it. The gas that we're inhaling right now, oxygen, it's nonpolar. It's literally O2, right? O double bond O dot 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 dot. This is nonpolar. And the oxygen is going into our blood, and our blood is mostly water. So we're told here gases generally have lower solubility in water than ionic or polar covalent bonds, right? Because gases are mostly nonpolar, and water is polar. So if that's the case, how are we alive then? I mean, right? How is this nonpolar gas, nonpolar, dissolving in our blood that's mostly polar? What's the secret? Pressure. Usually gases with high solubilities are reacting with water, but oxygen cannot react with water because it's nonpolar polar. They can't even dissolve in each other naturally. So, since we're not getting hotter just to dissolve it, the bottom line here is a higher pressure of oxygen causes it to dissolve in water. So we're able to influence solubility by increasing pressure. Okay? So in general, for gases, increasing the pressure of gas increases solubility. Okay? So higher pressure, higher solubility. And so increasing pressure results to increase solubility. And that's how we survive. And for us, the pressure is 1 atmosphere pressure of, the atmosphere. So what happens when people get older and they struggle with breathing, or even in the time of corona, right? If somebody gets infected and it's very hard for them to breathe and their lungs are not getting enough oxygen, what do they do at the hospital? Before they intubate, before they put them on the ventilator, what do they do? What is the number one goal when somebody gets corona? They give them oxygen, right? They give them not the atmospheric 1 atmosphere oxygen. No, that's too low. You're trying to increase solubility. That's the goal. So you see how the chemistry applies to the therapeutic actions in the hospital? They want to get a higher than 1 atmosphere. You're trying to save somebody's life here. So they give them a higher pressure oxygen dose. So it might be pure oxygen, maybe not pure, but a higher pressure than 1 atmospheric pressure. Well, actually, in the atmosphere, the whole 1 atmosphere is not oxygen. It's only 121, like 0.21 atmosphere is oxygen. So you're trying to get greater than this amount here to the person's lungs, so you can help them dissolve that oxygen in the blood, right? So they give them more oxygen, and that's the best thing they can do in that case. Understanding increasing pressure increases solubility. Same thing where they usually say grandmas, you see them in the mall carrying a little oxygen tank. Same thing. Increase pressure, increase solubility. With gases, sadly, if you increase temperature of gases, what we end up having is less solubility. Okay? Why is the temperature for gases bad for solubility? Remember, gas molecules love to move and they don't really have a natural compatibility with water. So gases will absorb higher temperature and leave the solution. And leave solution. So if your goal is to increase the solubility of a gas, don't add high temperature. If anything at all, cool it. So to increase solubility of gas, we can summarize what we just learned, right? These are your options. Number 1, increase pressure, or or I should say or number 2, decrease temperature. So the gas molecules cannot leave. So in this picture right here, I don't drink a lot of soda now. But when I was younger, I used to like soda a lot, especially like Pepsi or whatever, or one of them other fruity ones. If you want the gas, the carbon dioxide to really dissolve there and make it tart, then you put it in the refrigerator because the temperature, the lower temperature, increases solubility, and so less gas escapes. And if you leave it warm, then here's the gas escaping. And then sometimes you're sharing that, that big 1 liter bottle that you bought from dollar store, right, with your roommate in college, and then they're sloppy and they don't really cover it all the way. And then you go and try to drink the soda and it's flat, and you want to call them and say, hey, that was a $1 liter bottle, okay? You need to replace my soda because now it's flat. Thank you for nothing, Right. Because when it's flat, essentially all the carbon dioxide escapes. And so, yeah. So here's the thing. Hold on a second. I'm trying to see. Let me check how much time we have for this. Because it is time. I recognize it is time. Let me look at our schedule right here. Oh, course assignment. Because I'm trying to make sure we don't fall behind. Oh, my computer's so slow. So this stuff is due, oh, this weekend. But then your exam is, oh, okay, so we don't have to rush because we just have till this part here. Okay, so what I can do is I can continue chapter 13 on Thursday because we have a week before we do exam one, right? Okay, I was trying to make sure. So we're good. So instead of meeting tomorrow to catch up, I can continue with chapter 13 on Thursday, and then whatever we have left over, we'll finish next week, and then, we can go ahead and start the next part. Does anybody have any questions? So when we meet next on Thursday, we'll start here. We'll talk about Henry's Law, do the math. The rest of this chapter is mostly math. So I will start here. Okay. Any questions?
No.
Okay. And if you can't join the lesson but you still have a question, you can go ahead and email it to me and then I'll go ahead and address it in the lesson. Okay. Other than that, I can tell it's time for us to eat, right? Because y'all are kind of extra quiet, so it's time for food. Okay, y'all have a nice day. I hope your other classes are going well.
Thank you.
Okay, thank you. See you Thursday. Bye.